we started looking at fission and how it occurs. Um, we looked at this idea of the neutron being fired into this large nucleus on our planet. What we use mostly is uranium. Uh, what it does, atomic number 92. It's a massive nucleus. What tends to happen when you fire that neutron in there? The neutron to proton ratio gets too high. Also, the nucleus tends to vibrate like this and sort of distort, and it elongates. And we saw that by the fact that it elongates, that this nuclear strong force, which is a very short range force, doesn't really have the effect on the two ends as much anymore, and the coulombic repulsion does. And so what happens is the nucleus splits into two, and we have these two daughter nuclei, and this is fission. And the mass of the reactants is more than the mass of the products, and so we have energy released in this reaction. Yeah, it might be partly true, might be just a way to explain it. I can't tell you the exact. I imagine they can't actually see what goes on, to tell you the truth. This is what we imagine goes on. Yeah. Now, because I can't think of a way to test it. Maybe there is, but I can't think of a way with what we know to test what is going on exactly here. I think the reason they come up with that, the fact that this nucleus elongates, is firstly that it splits into two. That's pretty good evidence to say that it's elongating because of that strong force coulombic repulsion issue. Um, and also that the momentum of this neutron striking that nucleus there will cause it to vibrate a little bit more, okay? So we looked at a chain reaction. There's the first neutron, there's the uranium nucleus, splitting into two daughter nuclei, and we have two new neutrons, or three new neutrons, depending on the reaction, the nuclear reaction that we see. Um, these neutrons actually have between 1 and 2 million electron volts of kinetic energy, and they need to be slowed down. They can't be moving that fast. What will happen is if they strike a new nucleus, another uranium nucleus, they'll just either pass through it or deflect off of it, and no fission will occur, or fission is unlikely at this speed. So they need to be passed through this moderator. This moderator could be just water. Uh, we'll show you the inner workings of a nuclear reactor shortly, but this could be just water, it could be heavy water, it can be other things. It can be graphite as well, actually. But we'll just say that it's water or heavy water. Slows those neutrons down to about 10 eV. So reducing that by their kinetic energy by 1,000,000 times. And they go on to do more fissions. We have two more daughter nuclei, two new neutrons, and same again here. And of course that goes on and repeats itself many times. Yes.
So with the first reaction, there's two neutrons being released.
Yes.
So they'll combine with two other uranium nucleuses.
Yes.
So with the two other uranium nuclei,
Yes.
they form like two, then the other might be three, these three neutrons, or
Yeah, so it's not necessarily going to be these specific elements that we result, and it depends on several things. I imagine the speed of this neutron has a lot to do with it, and so for that reason, sometimes we're going to have two different elements created and three neutrons. And so there be the need, especially the need for the control rods in a nuclear reactor. Remember, we talked about this thing where a control rod can be lowered in, and it's computer controlled, of course, lowered in to basically absorb those neutrons and stop that reaction from going out of control. Okay, we'll talk further about that shortly. Does that answer your question, Paul? Um, certainly not. No, certainly not. And those daughter nuclei are not necessarily krypton and xenon. They can be other things. Yes, definitely. Um, we start with uranium-238 or 99 point. It's actually 99.3. I made a mistake in the last lesson. I'll change that now. Um, 99.3%, uranium-238, and 0.7%, still very low, U-235. This is the fissionable uranium, uh, fissionable isotope of uranium here. And so we need to enrich that, and we do that by passing it through or diffusing it. So passing it through a filter, so to speak. And remember I said about the uranium-238, of course, it's more massive than the U-235. The U-235 might pass through whatever it is that we diffuse it with, and so we can basically get all the U-235, mix it up with some U-238 in a 3%, 97% mixture, and we have fissionable fuel. Yes.
So the U-235 fissions because the U-236 is unstable due to too many neutrons.
Yes.
And how come U-238 isn't stable?
Well, it's. I don't know that it's necessarily more stable. I think. Yeah. Well, it's a good question. I don't know the answer to that question. This stuff here, with the speeds that we're talking about and the way we build nuclear reactors on this planet, U-238 is, in fact, there are lots of elements that are fissionable, but with the technology and the speeds of the neutrons that we're talking about, U-235 is probably the most efficient for us, I would say. Okay, that's the explanation I'll stick with. That's probably the best that I know, Andrew, at this stage. We'd have to look into it. So you only need 3% U-235. Some sources will say 4% U-235 for a fissionable fuel, and the rest, 97%, is U-238. And U-238 actually performs a function. It makes up the rest of the mass that is not fissionable, and so controls that reaction a little bit more. If you want weapons grade, you need to get 85%. This stuff's 85% U-235 is very hard to come by, lucky for us. This is the inner workings of the nuclear reactor that I showed you the other day. It's a little bit better a picture than this one here, but this might be the one that you see in the exam, if you were to see one, if they asked a question about it. You can see the control rods that are able to be lowered in between the fuel rods here. So this is the fuel. You can lower the control rods in between the fuel to stop the reaction, the chain reaction going out of control or overheating. We have coolant in and coolant out. Now, there's lots of shields. So this is generally a steel container. This is the core itself, encased in a steel container, watertight container, and also encased in meters of concrete. And they call this a biological shield or a biological barrier for the radiation. It stops all of the radiation. Over many years, this will break down, and there's the need for it to be replaced. If they, I think generally though they don't. This lasts the lifetime of the nuclear reactor itself, and when it's time for the nuclear reactor to be replaced, then everything gets replaced. So coolant in. This is our moderator also. It cools the core and moderates, so slows those neutrons down in between the fuel rods here. So just water going in here and water going out. It also basically what we're also looking to do is heat some water. And the pictures that I've seen, in fact, the heat exchanger is between the coolant, which is of course cool water coming in and hot water going out because it is a coolant. The heat exchanger is contained in the hot coolant water, and so that's where we get our energy from in the form of steam. Okay, what's next? Oh, so also I wanted to say about this U-235 nucleus. I'll get a picture of a nucleus again. I always go for the gold nucleus because I know it's got a good picture. This one here. So it's not gold anymore, it's uranium, because I said so. Now, so U-235 here, and neutron goes in. So what we have here, U235 has a high neutron to proton ratio, more neutrons than it has protons. Okay. The result is that we get, once we have fission occurring, once this nucleus breaks apart, we get two daughter nuclei. Which have the same high neutron to proton ratio. And they're going to be similar masses, but not exactly the same. This here, daughter nuclei will also have a high neutron to proton ratio. So what sort of decay are we going to see from these resultant daughter nuclei? More neutrons than they need. Yes, beta minus decay. Okay, so we're going to see beta minus particles coming off these nuclei. And I'll just write them in two different ways to remind you that we can beta minus particles. Back to our nuclear reactor. There's several components that you need to know. The core. So this is the container in which the nuclear reaction occurs. The fuel rods, we've talked about those a little bit, and they are rods. 97% will say U238, 3% U235, thereabouts. And essentially what they are is they're stainless steel rods that have this stuff packed into them. Yeah, they can be pellets or they can be in the form of powder. They can be in all sorts of forms. Yeah, I'm not sure what is the most common. I have heard pellets as well as pellets. So which contained in stainless steel rods. The moderator. And you know that can be water. It's water under pressure. Commonly water, just water, deuterium, or heavy water. So basically the water molecules are H2 molecules in that water, or graphite. The control rods. These can be raised or lowered to control, and I'll say, or maintain the reaction. And you can see very clearly in that FET simulator how they work. I had to move them in and out. You should have a go at that, moving them in and out just to keep that reaction occurring, or to stop it from going out of control, of course. These are made of. Uh, I've been I've seen boron lots. They used to be made of boron, and it's um boron in the form of a um, like a boron steel, high boron steel, or something like that. Boron itself as an element is not very nice to handle. Silver, cadmium, they can be made of lots of things. In fact, I looked at Wikipedia and the list is long. I guess it depends on the country in which you are as to what they're made of, and the availability of those metals or non-metals, whatever they may be. Um, Heat exchanger. Um, so the coolant is also uh, where the transfer of energy occurs. Transfer of heat energy occurs. Yes? No, this stuff will not turn into steam. So essentially, you could think of it like I'm not going to draw a very good picture. Let's see if we can find one, because the image in your book doesn't actually show where the heat exchange occurs. It just shows the coolant, which is the moderator. The internet, it's a little bit slow. Ah, yeah, this will do. I think it'll be big enough that you can see it. You can see. Oh, this one even, yeah, works. Okay, so we have the coolant. This is also the moderator going through and cooling that core, and of course taking away heat from the core, and then goes in, so that kind of gets passed through this water here, which would be clean water, which turns into steam and drives a turbine. Yeah, gets condensed. So how do you condense water? You cool it down essentially, and that's what this is, another cooler, a coolant here to cool that steam, to condense it, to reuse it. Okay. What do you mean? This water? Yes. Doesn't have to be water. No, it can be deuterium. I somebody I actually read somewhere that it could also be graphite. Now graphite's a solid, so I don't know a lot about that. So we need some form of heat exchange. We'll just stick to the fact that it can either be regular water as our coolant and moderator in the red here, coolant and a moderator in the red, and heat exchanger occurs in here, and that exchange goes on between this clean water, which is in the blue, which turns into steam, which operates a turbine. And this also, you'll notice this clean water here is independent of the radioactive stuff that is in here that goes around the actual fuel rods. and so is not radioactive or has low radioactivity because it goes into the outside world. This is where people have to go and maintain this stuff here. This stuff is only accessed occasionally when they need to change the fuel rods or repair something.
So the purpose of the coolant is actually to transfer energy, not
It does three things. Three things. It cools the core, takes heat away from the core. It moderates the neutrons, reduces their speed, and it also in taking the heat away from the core, it passes it over to this clean water here. Okay, three things as far as I can see it. In this case, yes. Now, somebody might refer to this stuff also as a coolant, or this stuff here as a coolant. So just be very careful. Um, it, it will be clear anyway in the question that you receive in the test, or in the exam for that matter. Heat exchanger. Coolant is also where the transfer of heat energy occurs. Moderation occurs. Of the neutrons. Also. Safety rods. We do need to mention these, and I haven't mentioned these yet. These are like the control rods, but kind of the last line of defense in case something goes wrong. These can be quickly dropped. To control or stop the reactor. And last thing they list here is shielding. And that's a steel container and meters of concrete.